Silicon appears as element number 14 on the periodic table, and is classified as a metalloid with the symbol Si. It is an earth-abundant element, commonly found in nature in the form of silicon dioxide, and may also be referred to as silica, or SiO2. The recycling and recovery of silicon and silicon dioxide may not be as popular in the headlines, but represents a mainstream core industrial element. In an effort to understand some of the key fundamentals that drive the waste and recycling industry, we have developed a website, waste.net, to act as a tool to assist in grasping the 4R strategy of reduce, reuse, recycle, and recover. Within the 4R's recycling and recovery sectors, we wish to distinguish between the recovery of the various forms of silicon dioxide that we encounter, and our efforts on separating and purifying SiO2 products, and then further, an additional important focus on the recycling, refining or converting of SiO2 into industrial grades of silicon. In an attempt to gain a better understanding of the handling of silicon and silicon dioxide, we recognize that it is an energy-intense process. In a multi-stage, wet chemical approach, operating in a corrosive environment utilizing both strong acids and strong bases, we may achieve an objective to obtain market-quality grades of feedstocks, of both silicon dioxide and silicon, within the Recovery 2.0 system. The Recovery 2.0 system is an innovative approach to manage the treatment of residual waste materials, in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy by using thermal reduction. Silicon dioxide is commonly encountered as silica sand and in common minerals such as quartz, feldspars, and sheet silicates known as phyllosilicates, such as mica, talc, adite jade, olivine group vermiculite, bentonite, and kaolin. Zeolite group and porcelain silicate ceramic materials, all are included as aluminum silicate residues. We intend to explore the realm of aluminum silicate residues recovery in greater detail at another time. In addition, we encounter all forms of glass and glass fibers which are silicon dioxide-based materials. We also would like to review some areas of glass recycling, fiberglass recovery, and the glass conversion field at some point in the future. The challenge of recovering all these various forms of silicon dioxide content materials, and converting them into a market grade of SiO2 quality feedstock is not a simple task. One approach to refining silicon dioxide is to use hydrochloric acid, which is known as HCl, in order to dissolve impurities such as aluminum oxide or Al2O3, and leave the remaining SiO2 as a solid residue. An alternative approach uses a strong base such as hot sodium hydroxide in a process where silicon dioxide dissolves into a sodium silicate solution, and many impurities, such as aluminum oxides, remain as a solid residue. The silicon dioxide may be precipitated out of the sodium silicate solution, with the use of hydrochloric acid, producing sodium chloride or salt water as a byproduct. The sodium chloride solution may be routed back into the brine electrolysis loop to regenerate sodium hydroxide. Either of these two approaches may produce a market-ready silicon dioxide feedstock that may be sold into external markets, or the SiO2 may be used as an internal feedstock, used to produce silicon. When we encounter silicon scraps, such as silicon wafer scrap or scrap photovoltaic cells, if the quality is appropriate, we may granulate those scraps and they become a direct silicon feedstock substitute. In the event that the quality of the available silicon scrap requires further upgrading, a hot sodium hydroxide leach bath may be used to dissolve the silicon wafer scrap, producing sodium silicate and a hydrogen gas byproduct. This reaction typically occurs at temperatures around 80 to 110 degrees Celsius. The conversion of silicon dioxide or SiO2 into a market-grade silicon, such as metallurgical grade or industrial silicon feedstocks, may be achieved through several optional pathway methods. Some of the common methods include carbothermic reduction, magnesiothermic reduction, or aluminothermic displacement. Carbothermic reduction is a method where silicon dioxide is mixed with carbon sources, coal, charcoal, or coke, and heated to high temperatures, in the range of 1500 to 2000 degrees Celsius, in an electric arc furnace. This method produces high-purity silicon and a carbon monoxide byproduct. Magnesiothermic reduction is a procedure where SiO2 is reacted with magnesium metal, typically in a sealed reactor or under an inert atmosphere, at temperatures in ranges of 500 to 900 degrees Celsius, followed by leaching with acid to remove magnesium oxide byproducts, to produce refined silicon. Aluminothermic reduction is similar to magnesiothermic reduction. This method uses aluminum to reduce silica, often used as an industrial symbiosis by including waste aluminum dross within the process. SiO2 is mixed with aluminum and usually a fluxing agent, such as calcium oxide is used to assist to form a slag, which produces a stable calcium aluminum oxide slag as a byproduct, while producing a quality silicon product. The reduction of silicon dioxide to silicon by displacement with aluminum in an aluminothermic reduction process may be achieved, with a stoichiometric balance of the molar ratio of 4 aluminum to 3 silica. In summary, the silicon and SiO2 recovery field represents an opportunity to avoid potential environmental residue liabilities, and may secure a supply chain for this strategic resource. Developments in energy harvesting, in areas such as the infrared spectrum, and salvaged heat management, may see new emerging innovative applications for recovered silicon-based materials. We intend to discuss additional facets of the energy and mineral resource recovery sector at some point in the future. Until then, please feel free to contact us at your convenience. Recovery 2.0 is a project developed by Waste.net, in an effort to reinforce our belief that as rational human beings, we must accept the ultimate responsibility to leave future generations with a safe and sound environment, and a world that has not been depleted of its resources. Please feel free to visit us today at www.waste.net.